So, we are going to see more examples of NP completeness reductions. But before I do that, I want to go back and do the reduction between vertex cover and independent set. And you had a question I did not answer properly, so let's do the reduction properly and I'll fix my answer. So, so we want to give a reduction from vertex cover to independent set. We've already seen the reduction, but I just want to formally go through it and fit it into my definition and argue that the reduction is fine, right? So, what is the input to the vertex cover problem? A graph, and the question is, what is the question? What is the output mode? Decision version. Is no, no. Is there a k sized vertex cover? So, the input is not just G, the input also contains a k. The question is, does there exist a vertex cover of size, let us say k? So, this is the problem. This is the decision version of the vertex cover problem, which we want to reduce to the decision version of the independent set problem. So, what is the independent set problem input? So, for independent set, the input is G, K. Again, you are given a G and a K, and the question is, does there exist an independent set of size K? Right? Similarly, for click and so on and so forth. So, now I said, well, you want to reduce from here to here. What was the reduction?
Is there a vertex cover of size? If you have the algorithm to find if there is a independent set of size k, if there is a vertex cover of size n minus k.
Okay, so by reduction, what is the definition of a reduction? It should take my input to this problem and convert it into an input to this problem, so that the S goes to S, no goes to no. Okay. So, my input to this problem is G k, and I want to reduce to an input to this problem. So, what should I reduce to? Complement of G? No, not for this problem. G. So, in fact, your complaint was you didn't change G at all, but somehow you changed the output, right? No, the input itself is G comma K, not just G, right? So, my transformation is G comma n minus K. So, yes, I did not change G, but now I am asking a different question here. Is there an independent set of size n minus K, right? That is it. That is my reduction. Okay. So, the F which you need for the reduction, which should take an input from here to an input here, is exactly, it takes G comma K, converts it into G comma n minus K, where n is the size of the vertex cover, right? N is the size of the vertex set in this graph. That is it. And the reason the whole reduction goes through and all that is because G has a vertex cover of size k if and only if G has an independent set of size n minus k, and the reason for this is because the complement of a vertex cover is an independent set. That's it. Okay, so is this clear now? It just fits into that definition of taking some input, converting into another input, right, such that S goes to S, no goes to no. Okay, good. So, let us get on to some other reductions now. So, we want to reduce SAT to the click problem, right. This is sort of counterintuitive because SAT is something about formulas, click is something about graphs. right? So we want to say that if you have a good algorithm for answering the decision version of the click problem, I can use that to solve satisfiability of a formula. Okay, so let's see how it should go. So how would you start? What is the f you are looking for? What should it do? What it transforms what to what? Be careful. What to what? Look at my direction. Boolean formula to a graph. Okay, the direction of the reduction is very important. Okay, so I want to take a formula here which is of this form, and what is the input to a click problem? Not just a graph and an integer, because the decision version asks, given a graph and the integer k, is there a click of size k, right? Because so I need to do this. So I need some function. I need to come up with this function. Okay, and what is the property I want the function to satisfy? Such that, what is the property I want? S should go to S, no should go to no. That's the property I want. Can you translate that? Exactly. F is satisfiable if and only if G has a click of size k. That is the property I want. G is in your hand, K is in your hand, right? You are given this formula, you have to somehow, so what we are doing is somehow encoding one problem into another problem. That's all we are doing, right? Then we can use an algorithm for a click to solve the SAT problem. So why do I even think that this reduction would be possible? What are these properties? Let's think about it, right? Before I construct the graph. What is it I want my assignment to satisfy? The assignment should simultaneously satisfy these M clauses. Okay. Well, here I want a click, a set of vertices such that every pair of them is adjacent. That's a property I want. Okay. There's something about, I want something to happen for all these vertices, something to happen for this assignment. Okay. So that gives me some high level connection that maybe this is possible. Okay. Let's just do one more step and say, I want an assignment. So each C1 is satisfied by something, some literal. Remember, each CI is a class of R's, right? It's like X3 or X7 bar or X2 bar or something. So one of them should satisfy C1. One of them should satisfy C2. One of them should satisfy C3. One of them should satisfy CM. That's what I want. I want some subset of variables. Okay. Now I'm trying to make the connection even more transparent. Here I want a subset of vertices which are mutually adjacent. Here I want a subset of variables such that, one would satisfy C1, one of them will satisfy C2, and one of them will satisfy CM. So now that gives me a direction of how I want to draw the graph, right? Okay, so let me try an example. Suppose C1 is X1 or X3 or X7. C2 is X1 bar or X3 bar or X5, and C3 is, okay. You are given this formula with some M clauses. I am going to construct the following graph. Remember, that's our goal, right? From the formula, our goal is to construct a graph with this property. So let's make the following attempt of this graph. So I'm going to say there is V1, V3, V7, V1 bar, V3 bar, V5, V2, V4, V6. So I'm going to construct a graph with these vertices. Okay. Even if V1 appears again somewhere else, let's do an example. Let's say X7. Then I will also have a V7 here. Okay, multiple copies of vertex. This is my entire vertex set. And for the moment, let's say that there are no edges within each set. So I have made some m. If there are m clauses here, I have made some m set of vertices. Okay, each set is the set of variables appearing in that formula, in that clause. Okay, now let's say there are no edges within each set, and there are all edges across each set, every pair of vertices. Okay, so I'm drawing all edges across, and this is my graph. Okay, and what is my intuition? Well, if the formula is satisfied, then in this set of variables, somebody should be set to true, right? Either that variable or its complement. If somebody here should be set to true, somebody should set to true, and I pick all of them, and I want to argue that they form a clique here. Clique of size what? No. Look at my graph. M, right? So remember I said G is your choice, K is your choice. It tells me now I am looking for an M clique here. Okay. So here is my intuition that if you have a formula which is satisfiable, there is some assignment that makes C1 true, that makes C2 true, that makes Cm true, which means that out of these variables, one of them is making C1 true. Out of these variables, one of them is making C2 true. And I'm going to pick those set of variables. Since I designed my graph in a way that there is an edge between every pair of these sets, they will form an M clique. Okay. So S will go to S. If you have a satisfying assignment, you will have an M clique. Now I also have to argue that no will go to no. One way to argue is that if you have an M clique, there is a satisfying assignment, right? Because if there is no satisfying assignment, I have to show that there is no M clique. One way to show it contrapositive is if there is an M clique here, I can pull out a satisfying assignment. Okay. But unfortunately, that's not true here because there is always an M clique here. Right? Why? Because pick one vertex here, one vertex here, one vertex here, one vertex here. The way I have drawn the edge, that will always be an M clique, whether or not that gives me a satisfying assignment or not. Okay. So I'm going to now modify this graph to meet my purpose. But let's see, when will an M clique here result in a non-satisfying assignment? Okay. So I pick a vertex here, pick a vertex here, pick a vertex here, and I say, oh, go and set that variable, that corresponding variable to 1, set the corresponding variable to 1, and that will satisfy your clause. When will it fail? Very good. So if I pick V1 from here, and I pick V1 bar from here, and you tell me that go and set V1 to 1, V1 bar to 1, there is a problem. I can't do that, right? So now how do I fix my graph? Graph is in my construction, my hand, right? Don't connect them. That's my graph, right? So given a formula, what is my graph? I have these partitions, set of variables for each clause. Draw all edges, no edges within each set. Draw all edges between them except when you have an xi in one set and xi bar in another set, don't draw an edge between them. That's my graph. Okay. So let's do the, right. So remember the graph, before you even know whether it is satisfiable or not satisfied, graph is, the moment you give the input, you should be able to construct this graph. So sat to click. So you are given this formula f, and my graph is going to contain these vertices. This corresponds to C1, this corresponds to C2, this corresponds to Cm. So the number of vertices would be the total length of this formula, right? There are number of variables are in C1, that many vertices are in this set, that many variables and so on. And the number of edges, so edge set would be, so let's call this some Vi corresponding to 1, and this is Vj corresponding to, So let's say this is some Vi and then this Vj. You have an edge Vi Vj. If Vi is in some Cx and Vj is in some Cy, x is not equal to y, and Vi is not, or the corresponding variable xi is not equal to xj bar. If these two variables are not contradictions of negations of each other, I will draw an edge. Okay. So, the moment you give me a formula, I have given my graph and I will give you an integer m, and the claim is f. Now, the claim is that f is satisfiable if and only if G has a clique of size m. And how do we prove this? Suppose f is satisfiable, then there is some assignment to this, all the variables of the formula, such that all these clauses are simultaneously satisfied. Now, I go to C1 and say, okay, who is satisfying you? Oh, x3 bar. I will pick x3 bar from here. And I ask C2, who is satisfying you? x7. So, I will pick x7 from C2, and so on and so forth. I pick those vertices. I claim that they form an M clique. Why do they form an M clique? Because there are edges between every pair of them, and nobody is a complement negated of the other, because otherwise you can't have those variables satisfying these clauses. And conversely, if you have an M clique, can the M clique pick two vertices from one clause, one set? Why not? Because I didn't draw an edge between any pair of them in each set anyway. It's a clique. So, there is an edge between every pair of them. So, if there is an M clique, it should necessarily contain exactly one from each of them. You can't have more because edges are not there within a set. It can't have less because it's an M clique. So, exactly one from each. Now, I go and set those corresponding variables. My assignment would be set the corresponding assignment that will satisfy my formula, because there are no conflict between these two things, because they form an M clique. So, what have we done? We have encoded the SAT problem into a clique problem. As a result, we have shown, since SAT was shown to be NP hard, we have shown that clique problem is NP hard, right? So, the consequence is that clique has a polynomial time algorithm implies SAT will have a polynomial time algorithm. Now, not only we have shown clique NP hard, we have shown independent set NP hard, we have shown vertex cover NP hard, because these reductions we have already seen the connection between these two problems. So, the corollary is, clique, independent set, vertex cover are all NP hard. They are also in NP, so it is NP complete. They are all in NP, because how do you show something is in NP? You just have to show that there is a witness for the S answer, which can be verified in polynomial time. So, the subset which is the answer is the witness here, and you can verify that they form a clique or an independent set or a vertex cover very easily. One important thing we need to check is that the reduction is polynomial time. Okay, this is very important. Often it's pushed under the rug. Well, how much time did we spend to do this reduction? What did we do? We created these sets, we created these edges. So, it's all, looking at this formula, it's just polynomial in the number of variables, number of clauses. Okay, let me just do. I wanted to do Hamiltonian cycle, but maybe I'll do one more. No, let's do Hamiltonian cycle. Okay. So, here is, okay, so let me do this intermediate thing. So, I want to show that 3 SAT is NP hard. So, what is the 3 SAT problem? Every clause has at most 3 variables. Okay. Now, we know that the general SAT is NP hard. I said this is a consequence of Cook's theorem, right? Now, which one implies what I want to understand, right? Suppose I show that 3 sat is NP hat. Does that immediately imply the general sat is NP hat? Or if I show the general sat is NP hat, implies this is NP hat? Okay, let me remove NP and then ask the same question, okay? Suppose I say that the general sat is hard. Does that imply 3 sat is hard? Or if I tell you 3 sat is hard, does that imply general sat is hard? Right? So the generalized versions are always harder, right? Because 3 sat means I am giving you more structure, somehow something which you may be able to exploit. So the more restricted version, if you show it is hard, that is a very strong result, because even with this extra structure, you are trying to show it's NP hard. Okay. So if I show this is NP hard, the general version is NP hard follows. But the general version is NP hard does not immediately imply this is NP hard. Okay. Let me just give you an argument of why, or give you a reduction. Maybe I won't give a complete proof of it. So let's say if I want to show this from general sat, what should I do? I want to give, so the proof I want to give, there exists a reduction, a polytime reduction. When I say reduction, here at least it's polytime reduction from general CNF sat. We are always talking about CNF sat again. Right? When I say 3 sat, I mean, the reason I keep saying CNF is there are more versions of sat where it's not necessarily, or you can have all kinds of functions of the 3 variables, but let's restrict to 3 CNF sat from general sat to 3 CNF sat. Right? It's always important to remember the direction of your reduction. You reduce from a known NP hard problem to your current problem. Okay. If I show this, then you would have shown that the current problem is NP hard. Okay. So what do I have to do? You take a general sat formula, it will have clauses of different sizes. If something has more than 3 variables, somehow I want to transform it, right? This is a function, the reduction function should transform it into another formula which has only at most 3 variables, but it has to do it in an equivalent way, that S should go to S, no should go to no, right? So let's say I have a clause without loss of some k is greater than 3. Okay. Now I want to just somehow break it up into clauses of small sizes, but still they are equivalent. Okay. So here is an attempt. So the way I am going to do it, for every such clause, x1 or x2, and I am going to introduce new variable y1, and right, this is all conjunction, y1 bar or x3 or y2 and x4 or y3 and dot dot dot. Somewhere I will have xk minus 1 or xk, and some bar will appear here. What bar will come? I think it is this. So I have taken this clause which has more number of variables than what I want, 3, and I have broken up into various clauses of this type. Is it clear what I have done? I've just thrown in new variables, and I've broken this big formula into formulas where each clause is at most 3 variables. Now I claim that these two are equivalent in the sense that if you have some assignment that satisfies this, there will be some assignment that satisfies this, and vice versa. Is the reduction clear? Okay. So let's see. Let's prove. I am not going to give a formal proof, but I'll just walk you through a reasonably complete proof. Suppose this clause, and now remember these variables, even though for simplicity I have written x1, x2, x3, some of them could be bars, could be x7 bar, x23 bar something, and you have to have a corresponding bars here. Okay. Right. So, suppose this clause is satisfied by setting x3 to 1. Okay. You do not know what satisfies this. Let us say x3 was 1, and I want to obtain a satisfying. Remember, these variables are also appearing in other clauses. So, you have to make sure that simultaneously it is not just this clause formula set of clauses I am worried about, outside also, right, because x3 was set to 1 to satisfy a whole bunch of clauses. So, now how do I translate it into an assignment? I do not want to disturb x3 because x3 has consequences outside. So, let us set x3 to 1, right. Now, what sort of freedom do you get? Yi's are your variables, you created them here. So, you can set them in whatever way you want. So, I want to say that if there is an assignment for the xi's, there is an assignment for the xi's and the yi's that will satisfy all these cases. So, what is a natural way to set what do I want to set y1, y2, y3? Can you give me an idea? See, since x3 is satisfying this, why don't I set y2 to 0? What did I achieve by that process? This guy is satisfied. Let me set y3 to 0. Let me set all the other yi's to 0. I managed to satisfy all these clauses, right. Since x3 is satisfying this, let me set y1 to 1. I managed to satisfy this. Okay. So, now whichever variable is set to 1, that gives me a room to set the yi's, so that some of the all the yi's after that I can set to 0, so that I can satisfy these guys, and set the remaining yi's before to 1, I can satisfy all of them. Conversely, I want to say that if this is not satisfied, if xi's are not satisfying this, there is no way I can use my yi's to satisfy all these clauses. Okay. How do I show that? Suppose all the xi's are 0. Okay, this is not satisfied. Let us see if I can play around with yi is alone to satisfy all these clauses. Okay. Since all the xi's are 0, if I have to satisfy this clause, y1 is forced to 1. Since all the xi's are false, y1 is forced to 1 if I want to satisfy this. Since y1 is false, y1 is true and x3 is false, y2 is forced to 1, right. If you follow through, all the yi's will be forced to 1, which means that this is also not satisfied. So, the only way you can satisfy all these clauses is sum of the xi's is 1. So, what have I achieved? I have taken a big class and translated, broken up into clauses of size 3 at most, such a way. Now, from here you have to write one more step to prove that if the original formula has a satisfying assignment, then this resulting formula has a satisfying assignment, and conversely. Okay, I more or less given a proof. Okay. So, this means that the SAT formula, even when I am restricted to at most 3 variables per clause, is NP hard. Now, you can ask, what about 2 variables per class, right? Can I do a similar kind of a reduction? If I have 3 variables in a clause, can I break it up into 2 and do this kind of things? We do not know, but this is solvable in polynomial term. If you have at most 2 variables in a clause and you want to do this CNF SAT, there are a number of algorithms, for example, including your directed reachability. You can convert it into a graph and translate it into some sort of a graph problem and solve it in polynomial time. Okay. So, this sort of contrast also gives you more evidence that NP hard problems are probably hard to solve, because you know that I am not able to do this kind of a reduction for 2 CNF, but in an alternate way I can show that actually 2 CNF SAT is in polynomial time. Right? This is a exercise. I am not sure it is in the problem sheet, otherwise we will add it. Okay, so let us move on from graph. So, we have seen some concrete reduction from SAT to graph problems.